Welcome to section 9.3, special cases of systems. You've seen this chart before. These are the exact same examples and exact same three cases that I talked about in back a couple videos ago. I believe it was section 9.13. Anyway, these are the three cases of graphing, and now we're going to talk about what it means to be dependent, consistent, independent, all that stuff. So let me first talk about what dependent is. Dependent is a system. A dependent system is a system equivalent to another system that has fewer equations. A consistent system is a system with one or more solutions. Let's start with consistent, actually. One or more solutions. So here's a system that has one solution that satisfies this definition, one or more solutions. This one also has one or more solutions. It has an infinite number of solutions, and you can even any point on this line satisfy this. So like the solution here, for example, when x is 4 and y is 0, when x is 0 and y is negative 4, when x is 6 and y is 2, when x is 7 and y is 3, when x is 8 and y is 4. These are all solutions to both systems. There's an infinite number of them. They're all plotted here on this graph. So if it has one or more, then it is consistent. And actually, I think I should amend this to say both dependent and consistent. Here, this is inconsistent because it has 0 solutions. It does not have one or more solutions. So it's not consistent, therefore it is inconsistent. All systems are either consistent or inconsistent. So the outer two are consistent and the inner one is inconsistent. It has 0 solutions. Dependent system. Now, dependent is a little trickier, and so basically what you need to ask yourself is every equation needed? And for example, here you need both of these equations to arrive at your solution. If you just have one of them, then you won't be able to get the solution that you have. But if you have every equation here is needed, then that is yes, independent. Independent systems are very, very good for producing solutions. So we like independence. Is every equation needed? Yes. Is it equivalent? Another way of saying this is it not equivalent to another system with fewer equations? And so here, for example, this is dependent. It's not independent. It's dependent, unlike this one. It is this. All of the solutions that are, all of the points that are solutions to this system here are all also equivalent to just x minus y equals 4. If you consider just x minus y equals 4, you get the graph that you need, and adding this additional equation here, 2x minus 2y equals 8, it's not really helping you find the solutions that you're at. This system of two equations is equivalent to just x minus y equals 4 all by itself. Therefore, it's dependent. Is every equation needed? No, you don't need both of these equations. You just need one of them to get all the solutions that are here. You can say it's dependent because it satisfies this definition. A dependent system is a system equivalent to another system that has fewer equations. This is equivalent to just x minus y equals 4. All right. Before I move on, I wanted to drop you an audio check and say that Casablanca was the Academy Award winning film in 1944. If you haven't seen it, classic film. Just an example. It's like one of the top 5 movies of all time, according to a lot of critics. And so just goes to show you that with great acting and great writing and great cinematography, you can produce a really moving movie. You don't need special effects. You don't need a whole lot of blood and explosions. Just a really amazing movie to watch. Characters and it'll bring tears to your eyes. It's good. Really good stuff. Watch it. A lot of people have and love it. So I wanted to make you a chart here, and this chart is organized. Let me show you how it's organized. We've got the same 2 questions from before. Here are 2 questions. Does it have one or more solution? If it's a yes, that means it's consistent. If it's a no, that means it's inconsistent. Is every equation needed? If it's a yes, then it's independent. If it's no, then it's dependent. I wanted to organize a chart to show you. You get a yes here and a yes here, that's what this would look like. A yes here and a no here, that's what this would look like. A no here and a yes here, that's what this, and then a no, two no's would be this one. So let's take a look. Let's take a look at this system right here, and we've seen this before as one of your examples. Is there one or more solution? When we solve it, we see yes, there is one or more solution. There it is, right there. There's the one solution. So therefore, it is consistent. Is every equation needed? Another way of asking that, is it not equivalent to any other system with fewer equations? Well, yeah, we need both of these equations. It is not equivalent to another system that has fewer equations. You need both of them here to produce the solution that you have. So it is independent. Let's take this one down here. Is there one or more solution? Well, when you solve it, when you graph it, you can see there's no intersections. There's a false statement, and you can say there's no solution. So therefore, the word for this is inconsistent. It has no solution. Does it have one or more solutions? No, it has 0 solutions. Now, is every equation needed in order to produce that result that it has 0 solutions? Yes. If you just try and take one of these individually, then you're gonna get lots of solutions, and they're all going to be plotted. Just the fact that it has 0 solutions, it requires both of these in order to get down to the result of 0 solutions. And let's take this example here. Is there one or more solution? Yes, you can see right here, when you graph these 3 equations, the 3 different lines all intersect at this same point. Technically, the artistry in your textbook is not all that great. You can see here that I think the publisher would have wished that they had gone through exactly the same point. That's really what they're talking about, what they're going for. If you graph them with a better grapher, like Desmos or a TI Inspire, then you can see that they will go through the exact same point. And it's labeled 5/2, 1/2. It has one solution, and there it is. So yes, it is consistent. One or more solution, yes. There it is, boom, graphed. Now, is every equation needed? No, you don't really need 3 lines to arrive at this solution. So the answer is no, you don't need all 3 of these equations. It's equivalent, it has the same solutions as a system that has fewer equations. So you could pick any 2 of these that you wanted, and you would still arrive at the same result, the same solution and the same number of solutions. So you could just pick these top 2 equations, and that would be the equivalent system that has fewer equations. You would have to say, an alternate way of saying it is it not equivalent to another system with fewer equations? No, it really is equivalent to a system with fewer equations. So therefore, it's dependent. This 4th case is really very rarely discussed, and I had to really look for it. But if you check out in the problem set, page 581, number 23, we get the double no. Is there one or more solution? No. Is every equation needed? No. And let me tell you why. First of all, it has no solution because if you choose 4 different numbers, or any 4 numbers, and then you add them all up and you get 4, then you try and add them all up again, you can't also get 3, and you try and add them up again, you can't also get 3. So therefore, it has no solution. It is inconsistent. It has 0 solutions. Now, is every equation needed in order to produce that result? No, you don't need this bottom equation. It's a duplicate of the middle equation. So if you wanted to, you could rewrite this system with just the top 2 equations and still produce the same result of no solution. So is every equation needed? No, it's dependent. It is, in fact, equivalent to another system with fewer equations. You could do this whole problem again with two equations and not 3. So that's your vocabulary, and I hope the chart is useful. I look forward to talking more about it. Send me an email or talk about it in class. Let's let me give you an example of how the SATs test you on something like this. This is a doozy. I wrote this particular problem based on what I saw in lots of other things. So, for example, they will give you fractions. Here, I don't see a fraction on anywhere in the chart. These are all examples in the book, but on the SATs, there could be fractions. They could start out with unsimplified equations. Now, all these are super simplified, and that's fine. But you look at something like this, 10x over here, 6x over here, there's an additional step of having to simplify your equation before you even get started. The equations could be in word form. Here's one. If m is n minus 1/2. It just throws you for a loop. It's like, what? What was that? And then as soon as you translate it into an equation, like down here, m is n minus 1/2. I think I wrote it better somewhere else. But anyway, m is n minus 1/2 is an equation in word form. It is dependent in that they give you more equations than you need, and there are infinite solutions. So although it is consistent, there's not just one solution. There's a lot of solutions to this. And then there's, on top of all that, there's an equation for an answer. So like they want to know what is y minus x. And at the end of all this, you're going to be able to say, well, y minus x is equal to a number. It doesn't tell you what x is. It's like we don't end this by knowing what x is or what y is, but we can say that y minus x is a number. So, first, they're given these two equations, and it says in the equation above, m and n are constants, meaning you can treat them like numbers. We're not trying to graph m and n. We're trying to just pretend that there are really numbers here, and maybe you have to figure out what they are. If m is n minus 1/2, then what is y minus x? So we can start off with this unsimplified equation, and the first thing I did was combine, so you subtract 6x from both sides so that it's simplified as much as possible. And then we get 4x minus 14 equals 2m. And you know what? It'd be easier to divide all the terms on both sides by 2. So you get 2x minus 7 equals m. Similarly, on the second equation, we could simplify that. I see a 4y and a 6y. Let's subtract 4y from both sides. We get n is equal to 2y minus 7. Great. Now that we have simplified equations, I'm going to write my knowns and unknowns. I know that m is equal to 2x minus 7. That's what I got here. I know that n is equal to 2y minus 7 here. And I know that m minus n is equal to 1/2. M is n minus 1/2. I think I rearranged it already. I didn't show that work. But you could say m equals n minus 1/2 and then rearrange it to get this. So I'm going to use some substitution. Oh, and then unknown, very important. Figure out what you're looking for. Y minus x. I have it here. You could have even put write down a is equal to y minus x, and that would have been fine. Like I'm trying to find a is, and a is y minus x. But that's introducing another variable. Maybe it's simpler just to say I want to know what y minus x is right here. Anyway, starting with here, I'm going to replace m and n with what I know them to be in terms of x and y. So just to zoom in a little bit. And it's no longer m minus n, it's 2x minus 7, which is what we know what m is, and then minus 2x minus 7. These second parentheses are absolutely required, and I just recommend putting these parentheses in out of good habit because that helps you proofread all your work. And the more parentheses you use for a substitution, the more likely it is you'll remember to do it when you actually really need it. So 2x minus 7 minus, and then distributing the subtraction here, you get 2y plus 7. See, if you forget these parentheses, this might be, my apologies, this should be a 2y minus 7, as you see here. Anyway, if you forget the parentheses, then although this 2y would come out correctly, this minus 7 would not, and it's a big mistake that students often make. So then we get negative 7 and then positive 7. They actually cancel out, and you're left with 2x is minus 2y is equal to 1/2, and then divide both sides by 2. You get x minus y equals 1/4. Whoa! You might think that that's where we want to stop. X minus y is 1/4, but what we're looking for is y minus x. And I know that if you multiply all the terms on both sides by -1, then you'll be able to switch things around. Negative x plus y is equal to -1/4, or rewritten like we're looking for, we have y minus x is equal to. You tell me what that is. What is the answer? And there it is. So I would just want to remind you that this is consistent and dependent. And I've seen things like if they're looking for testing on vocabulary, which they rarely do, they could say, which of these statements is true? Does it have one or more solution? Does it have is every equation needed? And that would be part of your multiple choice. Anyway, I expect that you might have some questions. Feel free to bring them to class or send me an email. You can start 9C and do the first problem, and I'll see you around.